Alright, it's been a while since I've done this. Get together. Chapter 2, Instructions, Language of the Computer. 2.1, Introduction. 2.2, Operations of the Computer Hardware. Skip over this. Introduction. To command a computer's hardware, you must speak its language. Read most of this. Introductory bit. Here's a nice little list. Okay. 2.3. Operands of the computer hardware. Unlike programs and high-level languages, the operands of arithmetic instructions are restricted. They must be from a limited number of special locations built directly in hardware called registers. Registers are primitives used in hardware design that are also visible to the programmer when the computer is completed. So you can think of registers as the bricks of computer construction. The size of a register in the MIPS architecture is 32 bits. Groups of 32 bits occur so frequently that they are given the name word. In MIPS architecture, word. Definition. Word. Group of 32 bits. Bits. 32 bits. Bits. So would it be right to say that a word is a register? Word. A register. Or rather, a register can hold a word. Only one word. The size of a register is 32. 32 bits is a word. Register holds a word. No, register holds word. Holds word. Word. Let me look at my homework real quick. I need to register right now. Section am I in? .003. Unlike program. One major difference between the variables of a programming language and registers is a limited number of registers, typically 32 on current computers. Thus, continuing in our top-down stepwise evolution of the symbolic representation of the MIPS language, in this section we have added the restriction that the three operands of MIPS arithmetic instructions must each be chosen from one of the 32-bit registers. The reason for the limit of 32 registers may be found in the second of our three underlying design principles of hardware technology. Design Principle 2, smaller is faster. A very large number of registers may increase the clock cycle time simply because it takes electronic signals longer when they must travel farther. Guidelines such as smaller is faster are not absolutes. 31 registers may not be faster than 32, yet the truth behind such observations cause computer designers to take them seriously. In this case, the designer must balance the craving of programs for more registers with the designer's desire to keep the clock cycle fast. Another reason for not using more than 32 is the number of bits it would take in the instruction format, as section 2.5 demonstrates. Chapter 4 shows the central role that registers play in hardware construction. As we shall see in this chapter, effective use of registers is critical to program performance. Although we could simply write instructions using numbers for registers, from 0 to 31, the MIPS convention is to use two-character names following a $sign to represent a register. 2.8 will explain the reason behind these names. For now, we will use $S0, $S1, ... for registers that correspond to variables in C and Java programs, and $T0, $T1, ... for temporary registers needed to compile the program into MIPS architecture. Example: compiling a C assignment using registers. It is a compiler's job to associate program variables with registers. Take, for instance, the assignment statement from our earlier example. The variables f, g, h, I, and j are assigned to the registers S0, S1, S2, S3, and S4 respectively. What is the compiled MIPS code? The compiled program is very similar to the prior example, except that we replace the variables with the register names mentioned above, plus two temporary registers, T0, T1, which correspond to the temporary variables above. Adding the operands in the brackets, and then finally subtracting the final operation of the expression. Memory operands. Okay, this is a difficult thing. Memory operands. Programming languages have simple variables that contain single data elements, as in these examples, but they do not have more complex data structures, arrays, and structures. These complex data structures can contain many more data elements than there are registers in a computer. How can a computer represent and access such large structures? Recall the 5 components of the computer introduced in Chapter 1 and repeated on page 61. The processor can keep only a small amount of data in registers, but computer memory contains billions of data elements. Hence, data structures, arrays, and structures are kept in memory. As explained above, arithmetic operations occur only on registers and MIPS instructions. Thus, MIPS must include instructions that transfer data between memory and registers. Such instructions are called data transfer instructions. To access a word in memory, the instruction must supply the memory address. The instruction must supply the memory address. Memory is just a large single-dimensional array, with the address acting as an index to that array. Starting at 0, for example, figure 2.2, the address of the third data element is 2, and the value of memory 2 is 10. The data transfer instruction that copies data from memory to a register is traditionally called load. The format of a load instruction is the name of the operand the name of the operation followed by the register to be loaded. Then a constant and register used to access memory. The sum of the constant portion of the instruction and the contents of the second register forms the memory address. The actual MIPS name for this instruction, LW, standing for load word.